Lab 2, Motion of a Falling Object. Introduction. Our purpose in this lab is to observe, record, and analyze a sheet of crumpled paper in freefall and plot two computational models, one which only considers the gravitational force on our paper, and one which considers both the gravitational force and the drag force on our paper, and create position versus time graphs to compare to our observed position versus time graph. Models. We use the GlowScript program to model the freefall motion of our object, considering both gravity and drag forces on our objects. Fundamental physical principles. We identified that the system is the crumpled piece of paper, that the surroundings are the earth and air. We use the formula as Newton's second law, which says that force is equal to mass times acceleration. We use the velocity update formula, which says that the final velocity is equal to the initial velocity plus the net force divided by the sheet of paper's mass times the change of time. We use the position update formula, which says that the final position is equal to the initial position plus the average velocity times the change of time. We also use the drag force formula, which says that the drag force is equal to negative b times velocity squared. Our results we saw is that the observed position versus time graph looks really similar to our computational model where we considered both gravitational force and drag forces position versus time graph than the computational model where we only considered the gravitational force. For our experiment, we set the initial conditions as such. The initial position was set to the zero vector. The initial velocity was set to the vector 0, negative 1, 0. The mass of paper was set to 4.5 grams. The velocity was updated using the velocity update formula, and we updated the position using the position update formula. We identified the system as the crumpled up sheet of paper, surroundings as the earth and the air. The earth's gravity pulls the paper to the ground, while the drag force resists that motion and pushes upward. And as you can see in the picture to the right, we are tracking the paper's position in tracker. Initial conditions. So this is our initial conditions in the code. On the left, we have the initial conditions for the model that does not consider drag, and on the right, we have the initial conditions for the model considering drag. The primary difference being the difference in the value b, where it is 0 in the model not considering drag, and 0.015 approximately in our model considering drag. Here's our code where we're only considering FG. This code simulates a crumpled sheet of printer paper free falling from rest, when the only force considers the gravitational force for the first 0.6 seconds, which covers my 18 frames. I tracked in tracker, utilizing the position and velocity update formulas after setting Fnet is equal to negative mg. As you can see in the code here, to the right we initially have our initial conditions, we have our change in time, then we have g approximated to be 9.8, we have the j hat, which is the direction for our positive y-axis, we have b set to 0 as we're not considering drag, and then we have our computational while loop, which sets the net force to be the positive y direction times the negative mg. And then we update the position and velocity using the velocity and position update formulas. This is our code considering the drag force. This code simulates a crumpled up sheet of printer paper free falling from the rest and considers both the gravitational and drag forces for the first 0.6 seconds, which again covers the 18 frames I tracked in tracker. And we use the position and velocity update formulas and set Fg is equal to negative mg and the Fb is equal to b times v squared, and set the F net force to be Fb plus Fg. And here's our code to the right. It is almost exactly similar to the previous code except for two things. One, we approximate b to be 0.015, and then the second thing is we recalculate net force by adding a calculation for the drag force and adding that with the gravitational force for a new net force. Here is the models and graphs that we have. To the top left, we have in the yellow our observed position versus time graph. In the blue, we have the model where we consider drag. And in the red, we have the position versus time graph for the model where we don't consider drag. In discussion, the results. The observed position versus time graph is closely modeled by the computational model that also considers the drag forces, as drag force is negative b times v squared, after setting b to 0.015, and has more of a linear model. The predicted model only considers Fg has more of an exponential drop and stops modeling the observed graph relatively early. Some possible sources of error in this lab are human error in tracking, not a perfectly zero force in the y direction drop, and maybe we misapproximated the b value slightly for drag force. And here's our graph to the right again. Conclusion. What does it mean? Examine the velocity versus time predicted by your models and without drag. Which models, if any, predict a terminal velocity? So our model where we consider the drag force, which takes the net force as gravitational force plus the drag force, predicts the terminal velocity. Net force is zero when at terminal velocity, as the gravitational force is equal to the drag force, just in opposite directions. What if the object was initially thrown downward? Would the terminal velocity in this case be the same or different from the case where the same object was initially dropped from rest? The terminal velocity would still be the same, as that is only dependent on mass, not initial velocity. Thank you.